Today we're going to look at a number of concepts to do with climate, and they're going to be very important for us to understand the thermal climate balance model, which we'll study next.
So let's begin by talking about the three different ways that thermal energy, that is heat, can be transferred from one location to another or from one body to another. For our purposes, the most important method will be radiation, and we'll be talking about blackbody spectra, etc. For right now, I just want to mention that all objects emit some electromagnetic radiation. And then this radiation can be absorbed by other bodies and the heat can be transferred. So light from the sun reaches us via electromagnetic radiation. And as it turns out, the region of the electromagnetic spectrum that's most effective for transferring heat energy is the infrared region. Conduction is very common. If I were to take my hand and place it on a cool desk, we would get conduction. And what's going on in conduction is that the molecules in my warm hand have lots of thermal energy. They're vibrating a lot, big vibrations. Whereas the molecules in the cool table have smaller vibrations. But when those big vibrations are right up next against the small vibrations get bigger and the big vibrations get smaller. And that is to say that heat's being transferred from my hand to the table via conduction. So conduction occurs via molecular interaction. And in most cases, that means molecules are vibrating against each other. The third method is convection. An example of convection is when you put a pot of water on a burner. What happens is that the molecules at the bottom get hot. And that causes the liquid to expand. So we have lower density at the bottom of the pot. And of course, a liquid with lower density will rise to the top, and we'll get what's called convection currents. And they can occur in
gases and liquids. So it's really all about the bulk motion of particles. So whereas radiation doesn't require any particles at all, and conduction requires particles that are next to each other so that they can bounce off each other and transfer energy, convection requires that particles can move around. So it only works in liquids and gases.
We said that we're mostly going to talk about radiation as a mechanism of heat transfer in this video. And the most important radiator of electromagnetic waves for our purposes is, of course, the sun. And in a previous video, we talked about this solar constant. We said S was equal to 1370 watts per meter squared. So it's really an intensity. And what the number represents is if we were to take a 1 meter squared piece of cardboard and face it directly towards the sun, and we're going to neglect any effects due to the Earth's atmosphere, then we would find that about 1370 watts would be striking that 1 meter squared piece of cardboard. So if we want to determine this number here, what we need to do is imagine a big sphere centered about the sun with the Earth passing through the surface of the sphere. So of course the radius of the sphere is going to be the Earth-Sun distance, 1.5 times 10 to the 11th meter. That's our radius of the sphere. And what you want to notice here is that all the power coming from the sun has to go through that sphere. It's all radiating outwards. It all has to pass through the surface of the sphere. So if we want to figure out what fraction of the sun's power strikes this 1 meter squared piece of cardboard, then we just need to take the power of the sun, the total power being radiated outwards, and we multiply it by the fraction that would strike our 1 meter squared. That would be 1 meter squared divided by the total surface area of the sphere, which would be 4 pi r squared, where r is the distance from the Earth to the Sun. It turns out the total power of the Sun is 3.8 times 10 to the 26 watts. So we need to multiply that by 1 out of 4 pi times this Earth-Sun distance, 1.5 times 10 to the 11th squared. And if we do that, we should get this solar constant, 1370 watts per meter squared. Now the path of the Earth around the Sun isn't perfectly circular, it's somewhat elliptical. So this is kind of an average value here. The actual value would vary by about 6% due to the variation in distance from the Earth to the Sun on that elliptical path. So this solar constant of 1370 watts per meter squared is the intensity from the Sun at the Earth, but that assumes that there is no atmosphere at all. That's just the sunlight hitting directly. The intensity will drop down to about 1,000 watts per meter squared if we add the atmosphere. So this would be on a perfectly clear day with direct sunlight. It'll drop down all the way to about 2 watts per meter squared if we have a very cloudy day. And we usually take a value of about 170 watts per meter squared as kind of an average value. This takes into account day and night. Of course, the intensity drops down to 0 at night. Takes into account whether or not it's cloudy or not. And it takes into account the location on the surface of the Earth. So as kind of a typical value for calculation purposes, we usually use about 170 watts per meter squared. So let's use our typical intensity value to figure out how much energy would be received by our 1 meter square piece of cardboard directly facing the Sun over a period of one typical day. And you can express your answer here. It'll be easier if you express your answer in kilowatt hours. So pause the video, try the question, come back for the answer. So the intensity striking the Earth is this 170 watts per meter squared. Now if it's striking 1 meter squared of area, our power would be the intensity times the area. The area, of course, is just 1, so we're going to get 170 watts there. And being as I want to use kilowatts, I'm going to express this as 0.17 kilowatts of power striking our piece of cardboard. So the energy has to be equal to the power times the time. The power in kilowatts was 0.17 kilowatts. And the time, we want to express that in hours if we're going to use kilowatt hours. 1 day is 24 hours. So we multiply by 24, and we'll get an answer there of 4.1 kilowatt hours of energy striking our piece of cardboard each day. You're all probably familiar with the idea of hot things glowing. In fact, we often speak of something being red hot if it's so hot that it glows red. And if it glows white, we might say that it's white hot. So different temperatures will produce different colors at which things glow. Now, as it turns out, all objects glow. They all transfer heat via radiation. But usually you can't see that glow because the radiation's not in the visible spectrum. It'll be at a longer wavelength out of the visible spectrum, so we don't see the glow. So all objects glow, just not in the visible spectrum. Now we have something called a Blackbody radiation curve, and it's very good for describing the radiation coming out of a glowing body. So it's a graph of intensity versus wavelength. And what we do is we take some object, and in this case it's been heated up to 3 different temperatures. So it got heated up to 3000 K, 6000 K, and 12,000 K. So let's say we heat it up to 12,000 K, and we have a sensor that collects radiation when it's at about 2 micrometers here. So the wavelength would be 2 micrometers, and it would collect a signal. And the strength of that signal would be proportional to the intensity. So that would give us a point on our graph. So then we could take another sensor that is triggered when the wavelength is about 1 micrometer, and we could measure the strength of the signal at 1 micrometer. And the strength of the signal would be proportional to the intensity, so we get another point, and then we could continue this process and trace out the curve, and then change the temperature and trace out the next curve, etc. So there's several things that I want you to notice about this curve. The first thing is that the overall intensity is less for lower temperatures. That is to say that this 12,000 K curve is generally of a much higher intensity than this 6,000 K curve. The second thing I want you to notice is that the peak is at a lower wavelength, that is a higher frequency, for higher temperature objects. In other words, this peak here is at a shorter wavelength than this peak here. And this one that's at a lower temperature still, its peak is at a longer wavelength still. And the third thing I want you to notice is that the visible spectrum is a small portion of the radiation emitted. In other words, it's only light within this wavelength range that we can see. The frequencies are too high back here, and over here the wavelengths are too long, the frequency is too low for us to be able to see that radiation. For everyday objects that are at about 300 K, their blackbody radiation curve wouldn't be visible on this particular graph. It would start here at about 3 micrometers and just be the tiniest little blip, totally insignificant on this particular scale of intensity. One of the key features of the blackbody radiation curve that I wanted you to notice was that as we decrease temperature, if we go say from 6,000 to 5,000, the peak wavelength becomes larger, and it keeps getting larger and larger as we go to lower and lower temperatures. And it turns out there's a mathematical relationship between that peak wavelength and the temperature of our glowing body. And that relationship is called the Wein Displacement Law. And it simply says that the temperature will be given by this constant's in your data booklet, 2.89 times 10 to the minus 3, the units would be meters times Kelvin, divided by that peak wavelength. So let's try it out. If I take 2.89 times 10 to the minus 3, and I look at the 6,000 K curve, then the peak wavelength is at 483 nanometers, which is times 10 to the minus 9 meters. And if I work that out, I get about 6,000 Kelvin. So that means anytime I've got a blackbody radiation curve, I can always identify the peak wavelength and always calculate what the temperature must be. So it's a very useful tool. So why do we use this name blackbody radiator for glowing objects? Well, the truth is we don't call all glowing objects blackbodies. Blackbodies are kind of an idealization. And it's because we want to make a distinction between reflection versus emission. So for instance, here's a white sheet of paper. Why does it look white? It looks white because it reflects all colors of light. Here's another object that looks white, but it looks white because it emits all colors of light. Now, many objects would both be reflecting and emitting to determining its color. A black body is something that doesn't reflect any light. We want to make a clear distinction and talk about only light being emitted and not being reflected. So a black body is an object that only emits and does not reflect light. And of course, what color are objects that don't reflect light? They're black. So we choose this name, Blackbody radiator or Blackbody emitter. We said that the idea of a black body was really an idealization. So we'd like a number that will kind of tell us, compared to a perfect black body, how much radiation is our real body going to emit. And that number is called the emissivity. So the emissivity is a number that tells us how well a body approximates that of a black body radiator. So this number, the emissivity, is just going to be a number that lies between 0 and 1. If it's equal to 0, what we've got is a perfect reflector. Think of a mirrored surface. All the radiation that strikes that mirrored surface is going to reflect off again. If the emissivity is equal to 1, then we've got a perfect black body. That is, we've got a perfect absorber of radiation. A piece of charcoal would approximate that well. All of the radiation incident on a black piece of charcoal is going to be absorbed by the charcoal. And if the charcoal stays at the same temperature, there's going to have to be just as much radiation coming out of the charcoal as there is going in. It's going to get emitted at a longer wavelength. So the radiation is absorbed at one wavelength and then emitted at a different wavelength. The emissivity is really just a fraction. If I take a certain body, and let's say it's at a given temperature T, and let's make it spherical and we'll give it a certain radius R, then it's going to emit some radiation. And let's say the emitted power is equal to 3 units, just to make up a number. And then we take an ideal black body, and it's going to be at exactly the same temperature and have the same physical dimensions, the same size. If it's spherical, it'll have the same radius. And it would emit a certain amount of radiation. That amount is going to be larger. Let's say the emitted power is equal to 5 units. Then that would mean our emissivity would be equal to 3 divided by 5, or 0.6. So the emissivity is really just a ratio. It's the ratio of the emitted power of some body compared to the emitted power of a black body of the same temperature and physical dimensions. I'll just write R to represent that. Now, as it turns out, the power emitted by a black body is proportional to the temperature to the 4th power, but the temperature there has to be in Kelvin. And this here is called the Stefan Boltzman Law. Now, whenever two things are proportional to each other, we can write an equation by using proportionality constants. So we could say that the power emitted must be equal to some constant times the temperature to the 4th power. Now, of course, if our object's bigger, it's going to emit more power. And we suspect that the bigger the surface area, the more power would be emitted. And that's true. The emitted power will be equal to some constant times the surface area times t to the 4th. This constant here gets the same symbol sigma. So our emitted power will be equal to sigma here. That's called the Stefan Boltzman constant. and it has a value of 5.67 times 10 to the minus 8. So that's the Stefan Boltzman constant. This A is of course the surface area, and we're primarily going to be dealing with planets or the sun, so most of the objects we're talking about will be spherical. So for a spherical body, the surface area is going to equal 4 times pi times the radius squared. So you take any spherical black body, tell me its temperature and its radius, and I'll be able to tell you how much power it's going to emit. Now it's often very useful to take our Stefan Boltzman law and express it in terms of the intensity. So if this is our body and we'll say that it's spherically shaped, then we can imagine all the power being emitted from the center. And just like we did when we calculated the solar constant, we can calculate the intensity at the surface of our body. So that intensity would be equal to the power emitted, sort of imagining it at the center, divided by the surface area of the body. So we're going to get sigma A times t to the fourth divided by the surface area. Surface areas are going to divide out, and so we'd get the intensity emitted at the surface to be equal to sigma t to the fourth power. And now, because we know about emissivity, we can write the Stefan Boltzman law for bodies that are gray bodies, that is, non-black bodies. And then the power emitted by the body would simply equal the emissivity times the power emitted by the ideal black body. So that emissivity is equal to the power emitted by the body divided by the power emitted by an ideal black body at the same temperature. We can then look up the emissivities for various materials. Here's a table for most of the surfaces of the Earth, and you can see that most of the surfaces of the Earth have emissivities fairly close to 1. And keep in mind for these emissivities, and then keep in mind for these gray bodies, that the radiation curve is going to look just like the black body radiation curve, except it's going to have lower intensity. So it has the same shape, peak at the same wavelength, just lower intensity for a gray body compared to a black body. We were saying how for a gray body, some of the incident light is reflected and some of it is absorbed. So a certain fraction of the incident radiation is reflected and a certain fraction is absorbed. We have a quantity here called the albedo. We use a Greek letter alpha for it. The albedo is equal to the fraction of radiation that is reflected. So maybe there's 200 units of incident radiation and 120 units are reflected. That would mean our albedo is 120 all over 200, which would be 0.6. Now for opaque objects, all radiation is either absorbed or reflected, which means that the fraction absorbed is equal to 1 minus the fraction that's reflected. And we can take that a little farther. If all that is absorbed is emitted, then we can say that the emissivity must equal 1 minus the albedo. Here's some various albedo values for the various Earth surfaces. So snow, fresh snow especially, will reflect a lot of light. And notice here clouds as well. Fluffy white clouds will also reflect a lot of light. Ice doesn't reflect as much light as snow. Dark, wet soil is going to absorb most of the light upon it. And maybe somewhat surprisingly, the water absorbs almost all the light on it. Generally water is dark in color, so that means it's absorbing a lot of light. Okay, a few IB multiple choice questions here. Pause the video, try the question, come back for the answer. So we've got the same power, so the power of x must equal the power of y. Power is given by Stefan Boltzman Law, so sigma. And the surface area, this is a sphere, so that would be 4 pi rx squared times the temperature of x to the 4th power must be equal to sigma 4 pi ry squared times the temperature of y to the 4th power. Sigma and 4 pi are going to cancel out. I'll divide both sides by ry squared, so we'll get rx all over ry all squared is equal to 2y over tx to the 4th power. Y is twice as big as x in temperature, so we're getting 2 to the 4th power equals rx all over ry squared. So rx all over ry is going to be what? 2 to the 4th is 16, but then you've got to square root both sides. Square root of 16 will be 4, so the correct answer here is B. Another IB multiple choice question. Pause the video, try the question, come back for the answer. High albedo corresponds to something that's quite reflective. And out of these three surfaces, I definitely say that snow is the most reflective surface. The fact that it's white means that all the colors of the visible spectrum are reflecting off it. Now between ocean and desert, well, the ocean is fairly dark, a dark blue. So it's absorbing a lot of light. So I would say that the ocean has a lower albedo than the desert. And so the correct answer here should be C. Ocean, then desert, then snow in order of increasing albedo. Next question, pause the video, read it over, try it out, come back for the answer. So ice and snow has a lot of albedo. If that's reduced, the albedo is going to decrease. So the answer's got to be either B or D. Now, if albedo is being decreased, that means there's less reflection and more absorption. So we have to get an increase in energy absorption. So the correct answer here is B. So let's summarize the big ideas from the video. We started by talking about the three forms of heat transfer. We said we'd primarily talk about radiation, which is really electromagnetic radiation, but there is also conduction, which is about vibrating molecules vibrating against the molecules next to them. And there was also convection, which was about currents and the bulk motion of molecules due to density and pressure differences. We then talked about the solar constant, and we said that S was equal to about 1370 watts per meter squared. But that an average intensity would only be about 170 watts per meter squared, and that would be due to day and night and cloud cover, etc. We then talked about glowing objects and the Blackbody radiation curve. And we said that all objects emit radiation, and we could plot the intensity of that radiation against wavelength. And if we did that, we'd get curves that looked something like this. This top curve would be at a higher temperature, and this lower curve is at a lower temperature, but for the same object. We want to notice that we get more of this radiation when the temperature is higher, and it will be of a generally shorter wavelength. And we also want to notice that the peak wavelength shifts towards longer wavelengths as you go to lower temperatures. And there was actually a relationship between the temperature and the peak wavelength. That was the Wein Displacement Law, which said that the temperature in Kelvin would be equal to 2.89 times 10 to the minus 3 divided by that peak wavelength. We then talked about the Stefan Boltzman Law. The Stefan Boltzman Law said that the power emitted by a blackbody varied as the temperature of the surface in Kelvin raised to the fourth power. Or we could write that as P emit equals Stefan Boltzmann constant times the surface area, 4 pi r squared, if we have a sphere, times the temperature in Kelvin raised to the fourth power. And if it was a gray body, we could use something called the emissivity. So for a gray body, emitted power would be equal to the emissivity times sigma times A times t to the fourth power, where E is a number between 0 and 1, and it's going to equal the power radiated by the gray body divided by that would be radiated by a perfect black body at the same temperature and same physical shape, etc. And finally, we closed out the video talking about albedo. And this albedo was simply the fraction of incident light that got reflected. And if we have an opaque object, then the emissivity, the amount of light absorbed and then emitted, would be equal to 1 minus the albedo. And that's all for today, folks. Thank you very much.